So another compare and contrast slide that now is going to look at the anatomy of mitochondria versus chloroplasts. So let's start first with mitochondria, since that's something that's familiar to us. You know, we've already finished that learning unit. So when we learned about the anatomy there, we sort of drew some lines here to sort of represent membranes, understanding that these lines represent lipid bilayers and so forth. But as we're talking about the mitochondria here, we've got the outer mitochondrial membrane, okay, the inner mitochondrial membrane. And I don't know if we mentioned this when we were doing our anatomy of mitochondria, but just reviewing or introducing if we didn't. This inner mitochondrial membrane is highly folded to create structures that we call cristae. And the reason that we do this is all of this beautiful biochemistry that happens in the inner mitochondrial membrane. If we fold it back and forth on itself, we create a lot more surface area to be able to do a lot more of that biochemistry. So those are the two membranes that we have, the outer mitochondrial membrane and the inner mitochondrial membrane. These are boundaries then for the cytosol, the inner membrane space, and then all the way on the inside is the matrix. And if we remember sort of where we think about proton translocation happening, right? If we are sort of at rest, we are going to have a low pH in the matrix. If, again, we are at rest. And that's because we're not moving those protons from the matrix into the inner membrane space and the cytosol, so we're not translocating those protons. So we're going to have a low pH, high proton concentration in the matrix. So if we think about proton translocation, remember we're going to be moving protons across the inner mitochondrial membrane. So we're going to be moving them in this direction, so protons moving in this direction when we're doing electron transport. I'm going to try to be consistent about anything that is with mitochondria. I'm going to use blue. And then when we have them moving back in the other direction, that's what happens during oxidative phosphorylation that allows us to synthesize ATP. Okay, so if we think about some hallmarks that we know of these two membranes, the outer mitochondrial membrane is highly permeable. Okay, and then we've got a highly impermeable and very protein-rich inner mitochondrial membrane. So this is impermeable and very protein-rich. Right? That's why we have it folded on itself, so we can create all of the surface area to embed more proteins. Okay? So that's again what we have with mitochondria. We've got our outer membrane, our highly invaginated inner membrane. We've got our cytosol out here. These two membranes separate and create the inner membrane space. And then all the way on the inside, we're going to have the matrix. So let's compare that then to what we see with chloroplasts. Well, chloroplasts also have two membranes. Give myself a little bit more space on the side here to write. So two membranes. Okay, I'm going to use abbreviations here down in my picture, but we'll highlight sort of where they are up top. So we've got the outer membrane. So again, that's the outer membrane up there. Okay, the inner membrane. So here we can see here's the inner membrane. Okay, those separate and create the inner membrane compartment. So that's the IMC, the inner membrane compartment. And this inner membrane is folded just like it is in, I shouldn't say just like, it's folded similar to how it is in mitochondria, but it creates a different shape. So rather than sort of folding it back and forth, you can think of it as sort of like poking in different discs is what we have. And we call these discs these thylakoid compartments. So these are folded in a way that creates a thylakoid compartment. Okay, so we can see that here we've got this thylakoid compartment. Now, we're going to have cytosol all the way on the outside, just like we do with mitochondria. So the inside, okay, matrix is equivalent to stroma, is what we have. So again, we've got our stroma here. That's all the way in the inside of our chloroplasts, okay? So that is going to be low pH, and we're not going to use necessarily the words at rest, okay? We're going to say low pH when it's dark out, because that's when chloroplasts aren't able to do their job, is when it's dark out, okay? So last piece, again, similarity to highlight here. We're going to move protons from the stroma into the inner membrane compartment. So again, we're going to move protons in that direction when we are doing chloroplast electron transport. So this is going to be electron transport in chloroplasts. And then moving them back in the other direction, this is going to be not oxidative phosphorylation, but photophosphorylation to be able to synthesize ATP. Okay, so one other piece here that I want to make sure to highlight is a big difference in what we have between mitochondria and chloroplasts, besides sort of the structure of that folded inner membrane, and the fact that we've got sort of some different names of things, okay? One of the other big differences is that this impermeable inner membrane, okay, is going to be more impermeable in mitochondria than it is in chloroplasts, okay? So using some colors here to highlight, this impermeability in mitochondria is both for concentrations and for charges. So we can build up a concentration gradient as well as building up a charge gradient with mitochondria. Now, with chloroplasts, it is only able to build up a concentration gradient. Okay, and it is not able to do a charge gradient. And we're going to see in a little bit, the reason for that is it is permeable to magnesium and chloride ions. So the ability to have those ions move freely across that inner membrane in relationship to their concentrations allow them to, or I should say not necessarily even their concentrations, to balance charge allows that charge gradient to not accumulate in chloroplasts where it does accumulate in mitochondria.